Basic factors affecting materials properties for space exploration designs and structures. Concurrent environments may be more detrimental to reliability than the effects of a single environment. As we have already presented in a previous video ESD on Week B, number 4, the technical rationale using the environmental factors combined in a relative altitude will help us also to frame the life cycles of the materials and structures until the specific requirements for a given spaceship design are met. NASA Reliability Preferred Practices for Design and Test, NASA Technical Memorandum 4322, explicitly describes some of these environment implications factors properly combined for materials design structures. Each environmental factor that is present requires a determination of its impact on the operational and reliability characteristics of the materials and parts comprising the equipment or material being designed. To this page, there is the overall tabular crossing of factors, from Earth and lower atmosphere in the vertical axis, in relation with the effects combined environments on the horizontal axis. Avoiding future processes escapes that are linked with the importance of testing and quality assurance for materials and embedded hardware systems engineering. Tabular crossings as a concept management function grid is also useful as one of the most practical reassurance relation and collaboration between a designer with a scientist assembler. It can be deployed within the same level of management command hierarchy, with high level of local department integration teamwork, increasing the reliability control for processes for tests and assembly performances. A special video from the NASA Lessons Learned is following for the case of NEN 1760, the rudder speed brake actuator from the Space Shuttle.
As managers and engineers look to the creation of a new exploration spacecraft, process control lessons learned during the Space Shuttle program can be helpful in preventing future process control escapes in other programs. The orbiter's rudder speed brake helps provide steering and slows the orbiter during descent and landing. Actuators inside the tail control the rudder speed brake panels. During a verification inspection, corrosion was discovered on the gears of the actuators. While investigating the corrosion, unusual wear and tear was noted on the gear set, leading to the discovery that the gears had been reversed during installation.
There are two sets of planet gears, and they have been installed in the reverse direction from how they should have been. Basically, they've been swapped out.
Painstaking and time-consuming examination of all of the actuators revealed the reversed gear problem in an actuator installed on one orbiter and one spare actuator assembly. The incorrectly installed gears reduced the overall strength margin of the actuator and could have resulted in a critical failure had the gears broken during flight. Fortunately, the affected flight actuator was located in a lower stress position in the overall actuator configuration.
We were lucky in this case that it was the lowest loaded actuator that was put together incorrectly, and as a result we didn't have any problems.
An investigation determined that during the original assembly of the gears into the actuators, technicians became confused because, although the gears were different, some looked extremely similar.
Further investigation showed that the actuator adjacent to the one that we found that was misassembled has the same type of gears in it, but they are mirror images of the upper actuator.
The robust actuators were able to function for over 20 years without a detectable problem. The mistake was not found sooner because the actuators were certified for the original flight life of the Space Shuttle, 10 years, 100 missions. So although the affected actuator had been installed for substantially more than 10 years, it had flown less than 30 times.
The initial requirement for the rudder speed brake system was 100 missions. However, the time for that was 10 years. Now, as it turns out, we went 20 years without looking at them.
All of the affected gears have been replaced and correctly configured.
As part of our mistake-proofing process, we actually went back and designed dedicated fixtures to each actuator that also have physical limitations, such that if you use the right tooling for the right actuator, you'll be unable to assemble it swapped out gear sets.
Process control is very important because when you manufacture something as critical as the flight control surface actuators for those things like the space shuttle, they have to work. And they have to work consistently, and they have to work every time. And if you have good process control, then you can assure yourself that you're going to get a consistent product every time you deliver a unit, and that it's going to work properly.
Process control must begin early in the design and engineering of flight hardware. Whether designing for new and improved space shuttle components, space station hardware, or future space exploration vehicles.
In your design, consider all the environments that you're going to operate in. It turns out for shuttle, because of its flight rate, the ground operational environment was really every bit as important as the flight environment.
Look at both the design process, the assembly process, and the manufacturing process to ensure a consistent product every time.
Create mistake-proof designs such that put components in that can only be installed one way, take out the human element that could potentially make an error putting that together.
Avoiding future processes escapes that are linked with the importance of testing and quality assurance for materials and embedded hardware systems engineering. On sequential system design for embedded hardware, check the following procedures for system specification, state transition table construction, state minimization and encoding, flip-flop selection, excitation output table derivation, logic simplification, logic diagram drawing. Avoiding future processes escapes that are linked with the importance of testing and quality assurance for materials and embedded hardware systems engineering. You cannot and should not trust the hardware you are given. You should always check for trust in microchip supply chain, backdoors, and trusted third-party apps and design tools. Improper design and implementation, hardware trojans, side channel attacks, physical attacks. Avoiding future processes escapes that are linked with the importance of testing and quality assurance for materials and embedded hardware systems engineering. Trust becomes an issue with offshore foundry and design complexity. Following the process diagram, you can check in each step which part can be characterized as trusted, untrusted, or either. The overall goal is the whole diagram procedure steps to be trusted,